Hi all, I'm Monisha from University of Strathclyde. We are based in Glasgow, Scotland. So just like to brief what my PhD is about, it's mainly I'll be focusing on the fatigue-based fracture mechanics crack propagation rate in high-strength steel is my kind of interest. So for this conference, I think I'm gonna compare the crack propagation rates in the ambient condition and also comparing that to the high-strength steels and the conventional steels. So yeah, the overview of the presentation is a quick introduction on what kind of the properties of my steel are and the methodology what I followed, because it has got both experimental and the numerical methods, just like the flow of the work which I carried, and then the results and comparing that with the answers, and then the conclusion and future work. So yeah, just to kind of give a update, it's a industry project. So I've still not have the permission to kind of reveal what exact grade is I'm using. So what I can say is just the yield strength of say the high strength steel is like 840 MPa. The other two, which I just say conventional steel, is because you can like find out more applications of the conventional steel. So that's the reason I just kept the name as conventional. When you kind of read the papers, you only get from the manufacturers, you get the basic material properties of the material. But we are more interested to kind of create a database that would like help the industry to mainly focus on the fatigue and fracture mechanics aspect of the material. And the other thing which we are interested is to see the influence of environmental conditions, say like it might be the effect of temperature, corrosion, and welding as well, which I'll be doing in my later stages of my PhD. And okay, to kind of measure the crack propagation rate, I'm like basically using the ASTM E647 standard, which has got both the front face technique and the back face. The reason why we are like comparing, we are using the back face strain gauge as well is to, because when we'll be corroding the samples in the corrosion test chamber, you can't actually use the CMOD gauge. So that's the reason we were like planning it would be easier to compare what the result we get from the front face and the back face. So we'll be having more confidence when we move to the corrosion thing. And yeah, I decided to use ANSYS Smart for my validation. Yeah. So speaking of the methodology, this is the figure 3 is the compact tension sample of my grade 1. And that's like a picture of my the sample in ANSYS. So the methodology is into two parts. First, we started with the experimental procedure, which includes the material selection, grade 1, 2, and 3, and the sample preparation, which is according to the ASTM E647, which also involves the attachment of the knife edges and the mounting of the strain gauge. And then the experimental setup, which mainly we use the Instron 8801, which has like the 100 kilonewton machine. And then we kind of decided the load and frequency for the test. Once I got my MNC values in the Paris core region, that was used in the ANSYS Smart and then the validation. So yeah, the other thing is my grade 1 has got a Mertensite kind of microstructure, which while reading the papers, I come across like even the microstructure has the influence on the crack propagation rates. I thought that would be an interesting term to include in my PhD. And I've met few person in the summer school who had like, but no one kind of concludes what exactly would be the influence of the microstructure. So I'll probably investigate that in the later stage. So my grade 1 is a Mertensite, and grade 2 and grade 3 are basically a ferrite pellet kind of microstructure. And the difference is like between the grade 2 and grade 3, I noticed is they have like the different percentage of perlite. But I did not have the time just before the conference to include what is the percentage of perlite in that. So which I'll be doing that in the later. And then my sample preparation is the ASTM E647, which I mentioned earlier, and my W is 40. The thickness of the sample which I chose is like 10 millimeter, and the initial notch was 10 millimeter, which we machined the basic structure with the CNC at the Strathclyde's workshop. And then the EDM was done for the initial pre-starter crack notch. And the other thing to highlight is the methodology is a bit different for grade 1 and grade 2. The grade 1 and the grade 2 and 3, because the grade 2 and 3 was carried out like probably 2 years before when I was like doing my master's, and that's like an old kind of test, which was basically my supervisor, and he thought it would be interesting for me to kind of include that as well in my PhD. So yeah, the machines are same for both. It's the Instron 8801 with a 100 kilonewton frame. And the methodology for the first grade one is we kind of did a step loading, which like say I initially started loading the sample with 9 kilonewton, and say probably after like 50,000 cycles when I see a bit of the crack propagation, and then I just reduce the load to 7 kilonewton. And then because basically with the grade 2 and 3, we didn't like do the step loading kind of thing. We kind of went with a load of 9 kilonewton. And because we are interested in like the equipments, what at the end, when we developed a product, would be like basically make sense to use the stress ratio 0. So that was the both common condition for that. And yeah, we attached a CMOD gauge for the front face, which has like the gauge length of 10 millimeter, and the back face was attached with a strain gauge with 120 ohm resistance, and that was like a quarter bridge configuration. And then once like the experiment was completed, we compared the experimental crack mouth opening displacements with the back face data results, and that are processed to obtain the crack length versus cycles. And then that gives my Paris law constants MNC. So this is basically from the ASTM E647 standard, and it's like a pretty direct. Once you open the ASTM standard, you kind of get the different methodology, which you could like use to measure the crack length and those things. So I will not like kind of speak more on that. It's like pretty direct. You could like refer the standard. So coming to my experimental results, the plot in the one in the figure 8 compares the crack length versus cycles. You kind of notice there is like different color ones that kind of mainly speaks on the load. What I use, like say the blue ones are 9, 7, and the 5 kilonewton ones. And the one which says the back face is like where I have compared the crack length, what I get from my CMOD gauge and the back face. So that's like a pretty good comparison. So we are like planning to use the same, like we'll be using the back face strain gauge technology when I do my corrosion test, which I'm like planning to do soon. And the one on the figure 9, which basically compares the crack length and cycles for my grade 2 and 3. And in that, we didn't use any like backface or anything, like the strain gauge was not mounted, and it was basically the CMOD gauge which we used. And coming to my DA by DN curves, it's like bit interesting for me, is because like the figure 10A, which is like for my grade 1, it has like, you can say, so the basically, if you ask me, why did you kind of play with the load? We just wanted to kind of spend more time with the sample, and we were like kind of interested in getting more points. This is like one of my first sample which I tested. So there's like a bit of mess in the data points in the initial condition. But then with the latest sample I tested, I kind of played about the sample with like for 4 or 5 days, and I could say like my curves, and I could like get a better data points. But the other thing which we are like interested is, you could see like some kind of a weird jump in the crack growth rate, and we are like kind of investigating what that the reason might be. One of the thing which we thought is like that might be a kind of the environmental noise or something. So we are like planning to use better shielded cables. And then as I mentioned earlier, which was like a quarter bridge kind of setup for the strain gauge, we'd probably use like a half bridge kind of setup, and hopefully we might get like a better, nicer, fancy curve. And these are like the summary of my MNC values. Like I think because my aim is to, my main project I'll be using the high strength steel, which is the grade 1. So I have like still many samples which needs to be tested. So, but this, the grade 2 and 3 was just like from a previous work. So I would probably not be much keen on investigating those kind of steels. But yeah, that's like the figure 11 is the Paris law for the MNC for grade 1. And then so once, yeah, after seeing the kind of the graph I got, I was like not confident, to be honest, to kind of to validate my MNC. So there was this analytical method which I used to kind of check my MNC values, and that was like pretty close to what we got in the experimental technique. That's when I started like moving to ANSYS, which is like a solid model. which I used a half symmetric model to kind of to reduce the computational time. And then the material is like, once I finished my experimental test, I had my MNC values. Then it's like easy for me to kind of put those MNC values. And if you notice, the MNC values in my is like with the different kind of the units. That's because with ANSYS, it's like in the same Pascal square root meter. So I thought to kind of make it easy, life a bit easier. So I just kept in those kind of value with the units. So yeah, for the meshing technique, like to kind of mainly be more precise at the crack tip, I use the sphere of influence method. And the crack is like an arbitrary crack with the smart tool, which is a kind of a nicer update from ANSYS that kind of automatically measures the as the crack propagates around the crack tip. And yeah, the loading conditions, like say if I'm like doing my load at like 9 kilonewton, then I apply like the equal loads and the displacement conditions. And that's the video of my variation of stress intensity factor in the sample. And yeah, this is the comparison of the stress intensity factor versus crack length. My figure 13, that's like the crack length comparison. A is for the grade 1. And because the different colors is like just based on the loading, what I have applied. And whereas for 13 B and C is the variation of the delta K with a crack length for grade 2 and grade 3. And yeah, this is like the comparison of my crack length versus number of cycles that I have like compared the one which I got from my crack mouth opening displacement gauge, and the one from the back face, and the one which I got from the ANSYS. Like for grade 1, it's like the comparison of all the 3 things. And for grade 2 and grade 3, because as I mentioned earlier, it's not like we didn't have the back face thing. So those are like my results. And this is like the interesting bit from the ANSYS Smart, where the crack kind of measures automatically. And I think you should have like seen, this is one of the video from my experimental thing before, like during the last stages of breaking of the sample. And as I mentioned earlier, what's interesting for me is also to do a microstructure study, which like how the crack propagation is affected by the kind of the microstructure. And yeah, so this is my discussion and conclusion. And the other, like the future work, I think will be interested more with the different environmental conditions and corrosion and welding. And then part of my PhD is to kind of do the fracture toughness test, I think, which I'll be probably doing after maybe in the next month. And yeah, like try to kind of reduce the experimental noise as much as possible. And yeah, that's me. Yes, thanks.